The first time I was on a plane, I remember watching the wing from the window. The aircraft accelerated hard, the nose lifted, and something that weighed an enormous amount simply stayed up. I knew the wings were doing it. What I didn't know then was that the wings were also quietly wasting a portion of the fuel it cost to do it. The fix for that waste is the one part of the wing everybody in a window seat has looked at without asking about. The tip, turned upward. Why is it there? Every time a wing generates lift, it quietly generates something else. A wing works by making air move faster over its top surface than its bottom. Faster air means lower pressure, and that pressure difference between the top and the underside is what holds an aircraft in the sky. That much gets taught in school. What's less often taught is what happens at the edges. The wing has tips, and at those tips, the high-pressure air on the underside doesn't simply stop. It spills sideways, curls around the tip, and rolls upward into the low-pressure zone above. Because the aircraft is moving forward, that curl gets stretched into a long, spinning column of air trailing behind each wingtip, a vortex. Two of them, one per side, rotating inward toward each other. They are large enough and energetic enough that the disturbed air they leave behind is dangerous to other aircraft. It's the reason air traffic controllers require a time separation before the next plane uses the same runway after a heavy jet. Those vortices are not a curiosity, they are energy. Energy the aircraft put into the air and never recovered. The wing is not only lifting the fuselage, it's also fighting continuously against the disturbed flow that its own tips are creating. That fight has a name: induced drag. Not friction drag from surface roughness, not form drag from the fuselage's blunt profile. Induced drag born from the act of generating lift itself. The heavier the aircraft, the more lift required, the stronger the vortex, the higher the drag. It is worse at low speed and high load. Precisely the conditions of a fully loaded aircraft climbing away from an airport. In cruise, induced drag accounts for a significant share of the total drag the engines push against. It is not a rounding error. A British engineer named Frederick Lanchester identified this mechanism as far back as 1897 and proposed fitting vertical flat plates to wingtips as a barrier to contain the spill. In theory, the plates weakened the vortex. In practice, they added structural weight and created their own surface drag, and the net benefit was close to negligible. The problem sat largely unanswered for most of the first century of powered flight. Not because no one noticed, because the fix had to do something active with the air, not just block it. And working out what that meant took time, an energy crisis, and a careful look at birds. That waste was acceptable until it wasn't. In the early 1970s, the aviation industry ran into fuel costs it had never seriously planned for. The oil crisis that began in 1973 forced airlines to treat previously acceptable inefficiencies as financial emergencies. NASA responded with a structured research effort aimed at aircraft energy efficiency, a program to recover the percentage points that had been left on the table. Richard Whitcomb was an aerodynamicist at NASA's Langley Research Center in Virginia. By the time he turned his attention to wingtip vortices, he had already reshaped commercial aviation twice, and the aviation community had learned to take his work seriously. What Whitcomb observed, or more precisely, what focused his intuition, was soaring birds. Eagles, vultures, and other large soaring birds splay their primary feathers upward and outward at the wingtip during flight. Each feather acts as a small individual lifting surface, fanning out at the tip. Natural selection, over very long timescales, had arrived at a solution to the same induced drag problem. and had been refining it far longer than we had. Whitcomb's conclusion was precise. The answer was not a flat plate. It was a small wing, aerodynamically profiled, angled upward, positioned exactly where the vortex was strongest, not to block the spinning air, but to interact with it deliberately. He published his analysis in 1976, predicting that a correctly designed winglet could reduce induced drag by approximately 20%. NASA, the US Air Force, and Boeing began flight testing in 1977 at Dryden Flight Research Center in California. The measured results confirmed the prediction. The lift-to-drag ratio of the test aircraft improved by around 7%. For a device that added almost no weight and required no changes to the engines, that was a number worth pursuing. But the explanation that usually accompanies it, the winglet reduces the vortex, drag falls, fuel is saved, skips the part of the mechanism that is genuinely counterintuitive. Here is where the standard account stops short. Yes, a winglet weakens the wingtip vortex. But saying smaller vortex, less drag, describes what happens without explaining why. The same way saying the engine burns fuel and the plane moves forward is accurate and completely unsatisfying. Think about the air at the wingtip. The vortex is already rotating. The air beside the tip is not flowing straight back in line with the aircraft. It has a sideways and upward component curling around the tip. Now place a small surface there, standing roughly vertical, angled into that rotating flow. From the perspective of that surface, the air is arriving from an angle, and a surface angled into a moving airflow generates lift, perpendicular to the local flow direction. Here is the part that changes the picture. Because the local flow at the winglet is rotated relative to the direction the aircraft is actually traveling, the lift the winglet generates is tilted slightly forward in the aircraft's reference frame. A component of that lift points in the direction of flight, and a force pointing in the direction of flight on an aircraft is, by definition, thrust. The winglet is not simply disrupting the vortex. It is partially converting the vortex's rotational energy into a small forward push, recovering something that would otherwise dissipate into the atmosphere as waste. This is why the winglet has to be a shaped airfoil with a specific profile and twist angle. A flat plate at the wingtip would disturb the airflow. A properly designed winglet positioned within the rotational field extracts something from it. Get the geometry wrong, and the winglet generates its own drag without producing enough compensating thrust. The commercial followed quickly. Boeing introduced the 747-400 in 1989 and McDonnell Douglas the MD-11 in 1990, both with winglets integrated from the initial design. Then came blended winglets, which curve smoothly from the wing surface rather than meeting it at a sharp fold. Boeing's 777X pushed the same logic into new territory. Its wings are long enough in flight to deliver a meaningful efficiency gain, but the tips fold upward on the ground to drop the aircraft into the lower airport gate category that gives it access to the majority of commercial airports worldwide. Each iteration refined the same underlying logic. Take the energy the vortex would waste and push some fraction of it forward instead. If a longer wingspan reduces induced drag, and it does, directly and significantly, the question becomes immediate. Why not just build longer wings? The answer is not aerodynamic, it's concrete. Commercial airports are built to dimensional standards that set hard limits on how wide an aircraft can be on the ground. The International Civil Aviation Organization defines aircraft categories by wingspan, and the widest category sets a hard ceiling. An aircraft whose wingspan exceeds the limit for its category cannot use the majority of airport infrastructure built for that category. Gates, taxiways, and aprons are all sized around it. An aircraft that cannot access the airports it needs to serve is not commercially viable, regardless of how efficient it flies. The winglet is, in part, an engineering response to this infrastructure constraint. It gives the wing a portion of the aerodynamic benefit of greater span by improving how efficiently the existing span generates lift. Without the aircraft physically exceeding its gate limit, the fuselage stays the same, the runway footprint stays the same, and the aircraft fits where it needs to fit. Boeing made this trade-off explicit with the 777X. That aircraft has wings long enough to deliver a substantial reduction in induced drag. But those wings fold at the tips during ground operations, reducing the footprint to fit within standard airport category limits. In the air, the tips extend and lock. On the taxiway, they fold upward. The mechanism exists because the optimal aerodynamic shape and the required ground footprint are two different things, and no one has resolved that tension, only managed it. So when you look at the curved surface at the tip of a modern commercial aircraft wing, you're looking at the intersection of several things at once. A physics problem identified before powered flight existed. An energy crisis that made solving it financially urgent. The anatomy of a soaring bird, one engineer's 3-decade habit of finding what others had missed, and the width of a parking space. Which raises the question I keep returning to. If we had designed our airports around the aerodynamics, instead of designing the aerodynamics around our airports, what would a wing look like today? Stay with Y Zone.